Hello and welcome to this talk at the CCGrid 2021. I'm going to present the work for CCGrid 2020 here. The title is Checkpoint Restart Support for Heterogeneous HPC Applications. It's basically GPU implementation of checkpoint restart for HPC applications. The work was performed by Konstantinos, Parasyris, me, and Leonardo Bautista. And the main contributions are multi-level checkpoint support for GPU applications into an open source library, highly optimized. So we performed 5 optimization steps to increase performance. And the handling of the GPU, CPU, unified memory, buffers is transparent for the user. Apart from that, we also implemented a novel multi-level differential checkpointing mechanism that can be applied to GPU and CPU buffers, is hash-based, and uses a GPU implementation of the MD5 algorithm. First, I'm going to look into the motivation. So why do we need GPU checkpointing? After that, I will go into the basics of multi-level checkpointing. What is multi-level checkpointing? After that, we will look into the GPU checkpoint implementation, and after that, the differential checkpointing implementation. So why do we need GPU checkpointing? Exascale systems will most likely have large parts of accelerators in the system. This is simply due to the fact that accelerators have much higher throughput than CPUs, and we need the performance of those modules to reach exascale. And accelerators can be GPU or FPGA or any other kind, but for the time being, GPUs are the most prevalent one and the most used one. So we are focusing on GPUs here in this paper. Recent studies have shown that failures on supercomputers are often originated by those accelerators, by GPUs. For example, here, this real example from Tsubame supercomputer showed that 40% of the failures were resulting from GPU errors, and only less than 5% from CPU errors. So we need a good mechanism to store or protect data from GPU buffers. Let's look into multi-level checkpointing. What is that actually? So the idea is extremely simple. We have several levels, and the levels are characterized by speed and reliability. The level of the highest reliability is typically the level with the lowest speed, lowest performance, and the level with the lowest reliability is the one with the highest speed. And libraries that implement multi-level scenarios are FDI, Veloce, and STR. FDI is maintained here at the Barcelona Supercomputing Center. Veloce is at Argonne, and the last one is in LLNL, California. And they all implement 4 levels of reliability. These levels consist of local checkpoint, partner checkpoints, encoded checkpoints, and checkpoints on the parallel file system. But more detailed, what is level 1 checkpoint? What is a local checkpoint that uses, it's a checkpoint that uses the storage device that is available on the node. This can be dynamic memory, this can be non-volatile memory, or SSDs. And this level can tolerate soft error failures. So when the node really crashes and is not responsive anymore, we cannot recover from that level. However, when we have a failure of the application due to some numerical error and the node is still up, we can recover from that. Level 2 is a little bit more sophisticated. We copy, or is more reliable, we copy the checkpoint locally. We copy it to a designated partner node. That can even tolerate node failures, because since we have the checkpoint on a partner node and this partner node is still up on the recovery, the MPI processes that were on the node that had crashed are now on another node, but they can recover because the checkpoint is still available on another node. Level 3 encoded checkpoints is already very reliable. The user can set a group size of nodes that perform encoding of the checkpoint files, and half of the group members can be recovered. So and the whole set of checkpoint files can be recovered from half of the group members. So and in that case, it does not even matter if the nodes that fail are consecutive or not. Any half of the members of the group can fail, and the checkpoint can still be reconstructed from the group members that have survived. However, the level of highest reliability is putting everything on the parallel file system. Since everything is on the parallel file system, even complete system crashes can be recovered. And obviously this is the most reliable one, but also the slowest one in most cases. In order to reduce overhead of those checkpoint level 2 to 4, we can also perform those levels in the background. So the first stage is storing the data locally to the file system, to the node file system. And the second stage is processing those checkpoints further to arrive to the desired checkpoint level, copying the checkpoint to the partner node, encoding the checkpoint files, flushing it to the parallel file system. This is performed in the background by FDI, by a dedicated MPI process. So since we have implemented our mechanism into FDI, let's look at a little bit of this library. The simplest use case consists of 4 functions: init, protect, snapshot, and finalize, where protect takes a pointer to a contiguous region and the size of this region. So we expose the data buffers that we want to protect in the checkpoint file to the library. FDI snapshot finally performs the checkpoint and the recovery. So but let's first of all the checkpoint. So the checkpoint levels can be set in the config file. So without recompilation, I can decide afterwards, okay, no, actually I want to have every half an hour level 1 instead of every half an hour level 2. And this can be changed afterwards, but in the config file what is provided. As well, on the failing of the application, this function as well performs the recovery. So FDI notices the failure of the application, that the application has crashed on restart, and performs all the measures to load the data from the checkpoint files to the buffers so that we can continue where we have left off. Okay, but let's move on. Let's go to the implementation. So what we actually did. We implemented, first of all, we implemented everything in a way that does not alter the FDI API. So everything what the library offers can be also provided to GPU checkpoint. The FDI runtime detects where the buffer actually is residing, and it can be from unified memory, device, or host memory. As an example here, we have 3 buffers: host memory, unified, and device. We allocate the buffers on unified memory, on device memory, so GPU, or host memory, CPU memory. And we can see here that we just pass the buffers, the size of the buffers, and the data type, without adding any information of where this data is residing, whether it's on CPU, unified, or GPU memory. So the library itself notices that. The user does not have to specify this. What we don't do is naive checkpointing, naive GPU checkpointing. So we do not simply take the data from the GPU memory to CPU memory and then from CPU memory to persistent storage. We do better than that. We have some optimizations. In total, we have 5 optimizations. The first one is that we overlap the streams from GPU to CPU. and from CPU to storage. The second one is that we compute the integrity checksum that FDI performs on the GPU. The third one is that we compute the integrity checksum concurrently to writing the data. So basically performing 1 and 2 in parallel. This is the third optimization. The fourth optimization is that we utilize all the available storage layers on the local nodes. This can be dynamic memory and SSDs or several SSD devices or NVMe devices. And finally, the synchronization of the checkpoint data to the file system we perform in the background. Okay, so let's look at the optimizations in greater detail. So first of all, we overlap the I/O streams. In practice, that looks like this, that we have a chunk. So the data, first of all, is partitioned, and the chunks are streamed to the CPU, and then they go to the stable storage. But when we write to the stable storage, we already get the second chunk from the GPU, and so on and so forth. So that in the end, we have some overlapping here from writing to stable storage and getting from GPU. The second optimization is we have to know that FDI performs an integrity check before the recovery. So in order to be sure that the data we want to recover on is consistent. And for that, we have to perform, we have to generate a checksum of the data that is stored in the checkpoint file. This is done using the MD5 algorithm and performed sequentially. So FDI as well splits the data in some buffers, and we in some blocks, and we write the blocks to the checkpoint file and in two steps. So we first we add the block to the hash of the block to the sum, and we write the data. But we can do better than that, because we can leverage, first of all, a GPU implementation of the MD5 sum and compute all those hashes in parallel on the GPU. In the first case, when we have everything already on the GPU, this is no problem because we have the data there, we partition the data, and we submit tasks that compute all the hashes of the minor blocks, and finally performs a hash on the particular sums to create one file hash. When the data is on the CPU, we have to copy the data to the GPU and there perform the steps that I just said. Yes. So, and the next optimization is that we perform optimization 1 and 2 in parallel. So we have the writing of the data, we write the checkpoint file, and we compute the integrity checksum concurrently. And to be more precise here, we don't collide with these both tasks are completely independent of each other. In the first task, we upload in the worst case. So in the case that we don't have everything on the GPU, we upload to the GPU. And in the second task, we download from the GPU. And since those streams happen on different types on the GPU, they do not collide. The second thing is that we don't compute anything on the GPU during the checkpoint because the application cores are idle. So we can use the GPU because we do not collide with any of the application computation. The next optimization is using several local devices. In our case, we have a cluster that provides access to 2 NVMe devices. NVMe is it stands for non-volatile memory. These are basically very fast SSD devices. And we use both of them. So we assign half of the processes to one and the other half of the processes to the other device, so we can write in parallel the checkpoint data to both of these fast I/O devices. And last but not least, we have the synchronization with the file system. So IO libraries typically work with buffers. That means that when we write the checkpoint file, the functions return as soon as the checkpoint data is pushed to the IO library. And the IO library uses dynamic memory, volatile memory for this. Only by issuing fsync, we can be sure that the data actually really resides on the file system. And this is quite important for us, because we can only assure that we have this checkpoint when the data is actually really pushed to this. So we have to issue this call. However, there's a library that offers the possibility to do that thread-based. So we do the synchronization of the file system in the background while releasing already to the application. So the application can continue while we perform the synchronization of the file system. And this turns out also to be the biggest speed up in the end. So here are the optimizations. First, the baseline is basically the overlap of GPU, CPU, and CPU storage layer. Then the creation of the checkpoint integrity sum of the GPU brings a speed up of 1.3. The next one is the concurrently performing 1 and 2, speed up of 1.3, so the same basically. And then we leverage 2 local NVMe devices. We can write up to those then really in parallel. This gives 1.4 speed up. And when we synchronize the file system to the background, actually that is what brings the most benefit. Okay, so let's look at the differential checkpointing implementation. There are 2 options. We can implement it by using the page protection mechanisms on the kernel layer. So to see that if has this page what we have in our buffers changed since the last checkpoint. We decided to use a hash-based approach due to some considerations that are better explained in the paper. So the data is partitioned into blocks, and each checkpoint, by the time of each checkpoint, we compute hashes of all of these blocks. And when the hashes of one block change to the hash from towards the former checkpoint, we write those data because we know, okay, the data in that block has changed, so we need to update the checkpoint file. We implemented, for this, to realize it, we implemented a file format that consists of several layers. Every layer corresponds to one checkpoint. So layer 0 is a plain checkpoint that writes all the data. The next checkpoint only updates the differences that corresponds to the layer 1, and the next checkpoint only writes the differences to layer 1, and so on and so forth, so that we have like after 5 checkpoints we have 5 layers, etc. We compute the hashes on the GPU, so we leverage the MD5 GPU implementation. The dirty blocks are appended to the checkpoint file, as I just explained, and this has several reasons. The most important one is that writing directly to the file is quite dangerous. Let's assume we have rerun already 15 checkpoints, and we update the file directly, and something happens during this write. Then the whole checkpoint file is destroyed, and we don't have any checkpoint anymore. So instead, we append the data so that when something happens, the checkpoint file does not get destroyed because the former layer is still intact, and we can truncate the file and still recover from the last checkpoint. So this is the most important point. The second point is also important because it is also more efficient to append the data. Since when we write directly to the file and we have, let's say, blocks of very small size, we have to update a number of blocks with elementary I/O operations. And we know that random writes are much slower than sequential writes. So, and what we do when we append the data is sequential writing, and we can use all the benefits of buffered I/O in that case. So it's also much faster. Let's look at some data. We can see that the overhead decreases linearly with the amount of clean data. In this plot, we have the percentage of dirty data actually. So when we have 80% of dirty data, we have to write 80% of the checkpoint data. And this is the speed linearly increases when with the less we have to write, obviously. So, and then also we can see that when we have lots of layers, we also have a higher benefit of this differential checkpointing because because we write less plain checkpoints. Because when there's a layer size, I don't know, I think I did not mention this, but the layer size, so the number of layers that can be contained in one checkpoint file is constrained by the user. So the user can tell, okay, I want to have 5 checkpoint layers, 10 or 15 checkpoint layers or whatever. And the lower the number of layers we have, the more frequent is the plain checkpoint write. So when we have to write 100% of the data. So obviously when we have a high number of layers, we have the best benefit. And applying the famous Young formula for the optimal checkpoint interval, we can see also that we have a much higher frequency of checkpointing when we only have 20% of changed data here. So every 200 seconds towards 320 seconds, we write the checkpoint. And this is also important because the more frequent we write the checkpoint, the less recomputation we have when upon the failure, obviously. Okay, so let's sum up. What did we do? We implemented GPU checkpointing for a multi-level checkpoint library without altering the API. And the paper we demonstrated, I didn't show all the plots here, but in the paper we have many plots that show the benefits of our implementation towards the naive implementation. And in addition to that, we implemented a differential checkpointing mechanism that leverages the hash sum creation on the GPU. Yes, and that's basically it. Thank you very much for listening to this talk. It was funded by the Legato project, the Barcelona Supercomputing Center, and the UPC. And thanks as well to CCGrid. And that's all. Thank you very much. Goodbye.